Dr. Vijay ma'am.
Ma'am, Jalashmi ma'am, am I audible, madam? Jalashmi
Yes,
ma'am?
sir. Yes, sir.
Okay, okay.
Sir, Sankaran sir, welcome sir. Dr. Sankaran sir.
Have we given the co-host, madam? Sankaran sir? I think you have to give the co-host, madam.
Sankaran sir.
Yeah. Sarah is going to co-host, madam. Sankaran sir, now, okay, we have given the co-host privilege to you, sir. Please turn on a video and...
sir, good afternoon, sir. Yes, sir.
Good afternoon, sir. Good afternoon, sir.
Yes,
How are you, sir?
I'm fine, sir. How are you, sir?
Yeah. I am fine, sir. Very thank you. Okay, I mean, for you to give the consent to deliver the talk in 1 week all in FDP, sir.
Yes,
Thank
sir.
you
Yes,
so
sir.
much.
Yes, sir. It's my pleasure.
Sir, thank you, sir.
Yes,
Thank you
sir.
so much, sir.
Yes, sir. Thank you so much. Yes, sir. Actually, there was a heavy rain, madam, still going on, so that I'm a bit late to come to the office.
Okay, sir. Okay, sir.
Heavy
Thank you
rain
so much,
today.
sir.
Yes, sir. Yes, sir.
And,
Sir, Tina ma'am, sir.
yes, sir. Madam, shall we start, madam?
1 minute, sir. 1 minute. 1 minute.
Okay.
Sir, am I audible? Sankaran sir?
Yes, ma'am. How are you, madam?
Yes, sir.
Good afternoon,
How are
madam.
you, sir?
I'm fine, madam. Good afternoon, madam. Nice to meet you.
Yes, sir. Thank you.
Shall we start? HOD sir. Ma'am, am I audible to you?
Yes, sir. Yes, sir.
Yes, sir. Okay, we'll start, sir. Yes, sir.
Very good afternoon to one and all present in the 1 week online national level faculty development program on advanced computational and experimental research in physics. So today is the third day. So we have Dr. K. Shankaran sir, senior scientist, CSIR, Institute of Minerals and Materials Technology, Bhubaneswar, Odisha. And he is going to deliver the talk on the topic microplasma materials, devices and applications. Now I invite Dr. V. Jayalakshmi ma'am to moderate the entire session.
Thank you, sir. Thank you, sir. It's my pleasure to introduce Dr. K.J. Sankaran, sir, Senior Scientist, CSR, Institute of Minerals and Materials Technology, Bhubaneswar, Odisha, India. His educational qualifications are: he completed his BSc in Madurai Kamaraj University in 2005, and he completed his Masters in 2007 in Anna University, and he completed his PhD in 2013 in Tsinghua University, Taiwan. He has research experiences from 2007 to 2009 as research assistant in Central Electrochemical Research Institute, Delhi, and from 2013 to 14 for postdoctoral researcher, National Tsinghua University, Taiwan, and 14 to 15 was a FWO Picasso Marie Curie postdoctoral researcher in Hasselt University, Belgium. In 15 to 18, he is again FWO postdoctoral researcher in Hasselt University, Belgium. In 2018 to 19, he did his postdoctoral research in the same university. His credential, he published 101 papers with 2 book chapters, and his H-index is 24, and his scientific awards are: he got in 2005, he was a meritorious rank student in 2005 in Madurai Kamaraj University, and in 2010, he got an outstanding PhD scholarship award in Tsinghua University, and 2011 Best Poster Presentation Award in Taiwan, and in 2018 selected by FWO to attend Euroscience Open Forum in 2018 for France, and 2019 Excellent Poster Presentation Award in NDNC 2019 Taiwan. His experiences are: he has experience in diamond thin film deposition using microwave plasma chemical vapor deposition system, including linear antenna microwave CVD systems. He skills in nanostructure fabrication using reactive ion etching technique. He also skills in experience in handling called NJBP UV mask aligner He experiences in designing and handling field thermionic electron emission and microplasma elimination measurements. He has skills in imaging with transmission electron microscopy, field emission scanning microscopy, and atomic force microscopy. He has hands-on experiences with X-ray diffraction, Raman X-ray, X-ray photoelectron, X-ray absorption, resonant inelastic X-ray scattering, and Fourier transform infrared spectroscopic techniques. He experiences in Hall, pore probe, and electrochemical measurements. Sir, we are happy to have you here, sir. The session is yours. You can take over the session, sir. Thank you all.
Thank you, madam, for your kind introduction. Again, I thank you all for inviting me for this the faculty development program. So I will share my screen now. So is my screen visible, madam?
Yes, sir.
So it's in full screen mode. I hope so.
Yes, sir. Full screen.
Yes, madam. So good afternoon, everyone, and myself, Dr. Shankaran from CSIR Institute of Minerals and Materials Technology, Bhubaneswar. So today I'm going to talk about the fabrication of the microplasma devices and the cathodes which we are using for the microplasmas, and what are the applications of the microplasmas devices related to the energy as well as the bio and as well as for the electronics applications. So before going to my talk, I would like to introduce about CSIR IMMT. The IMMT stands for Institute of Minerals and Materials Technology. With this institute is located in the middle of the Bhubaneswar. It's a very green environment, and it has a very good research research environment also here, with a very good we can say a sophisticated instruments with all types of characterization, basically for the minerals and the materials. And since Odisha is famous for the mining industries, here research is mainly going on the mines that we are collecting the materials from there, and we are extracting the minerals and the materials from those kind of mine waste. And there is a department called the electro and the hydrometallurgy, as well as for the minerals and the mines. And there is a department especially for the computational purposes. So here there are the departments that we are working on. Advanced Material Technology department that I am working now, and there is a central characterization department which has a sophisticated instrument starting from the microscopy to the spectroscopy. Also based on the if you are looking for some mineral based industry, that's also we have the sophisticated characterization units. And the metal chemistry department, they are working on the fundamentals of materials based on the chemical techniques. And we have a design and project engineering. They are also the engineers here. They are mostly working on the development of the industries for the upscaling the development of the products. And environmental and sustainability department, they are working on the water pollution, air pollution based research. And hydro and electrometallurgy and mineral processing department, these two departments of the core of IMMT, mostly working on the extraction of the minerals and the materials from the mine waste. And the process modulation and instrumentation, they are also modeling the work for the making up the lab scale, from the lab scale to the industrial scale. So I belong to the Advanced Material Technology department, and here I list out some of the activities. So the AMT department is the well-known department for the plasma-based techniques for the synthesis of the materials as well as for the applications of the materials based on the plasma. The Institute of Plasma Research, other next to the Institute of Plasma Research, AMT department having the most plasma-based techniques in India. And we are very much skilled in development of the thin films as well as some coating units we have based on the plasmas. Also, a group here in my department also working on the plasma processing of minerals, waste and special materials. And also a group here also working on the metals and alloy making, preparation of the carbides, oxide and nitride powders. They are mostly on the powder metallurgy area. And we have also a unit in our group. They are working on the failure analysis, deeply working on for the industry based we are getting projects from the industries. And we have also a microstructural and physical property studies can be carried out in my department for the natural gems also, that mainly other than the the National Geology Institute, we are the one having the sophisticated techniques which go for the defects in the gems, and we have advanced characterization techniques also in our department, basically FESEM, Raman, and FTAR, and also some other spectroscopic techniques. So today I'm going to talk about the microplasma. People, we heard about the plasma and what is microplasma. That is the new thing what we can do with the microplasma. So I will talk about how the basics of the plasma, how plasma can be generated in the lab, and what is microplasma and how the device can be fabricated. One of my PhD students has developed the microplasma device in my lab, and we are keenly working on to find the best cathode material for the microplasma, and what are the applications of the microplasma, and how we can characterize the properties of the cathode to be a very good cathodic material for the microplasma device. So these are the contents that I'm going to discuss today. So basically, what is plasma? So the plasma is nothing but this is the fourth state of the matter. We all know about the major three states, that is the solid, liquid, and gas, and the plasma is the fourth state. And if you can see here, the solid, which is at a low temperature, it will be in a solid form. Then we are supplying some temperature or maybe some energy, it may convert into liquid. And then once you supply some more high temperature, the gases can ionize, that becomes the plasma. That is the fourth state. So a very easy understanding can also be known from these schematic diagrams, in which the solid having the strong bonding in nature. Once it melts, it becomes the liquid. Then supply of some energy, it becomes like a gaseous state with no bonding. And then again supply some energy to that, it becomes ionization. That becomes the plasma. So the plasma contains partially or fully ionized gases having the electrons, ions, atoms, and molecules with nearly zero net electric charge. So we can also reversible this process, like plasma to the gas, gas to the liquid, and to the solid process. So we are focusing on the plasma here. So how a plasma can be generated, how we can make the plasma. This is a very easy process. Even we are working on the plasmas even in our household equipments also. So it is very easy. You can see this animation, that supply of some energy like heat or maybe some electricity. We can see here the gases inside a chamber get ionized. That ionization results in the formation of the plasma. So supply of energy is important in terms of heat or supply some voltage to that. So the ionization gas mixture consisting of ions, electrons, and neutral atoms in the plasma. So if you can see here in the earlier one, there is some plasma color has appeared. Also, even in this sputtering chamber or maybe the reactive ion etching chamber, there is a color of the plasma. How a plasma gets this color? That is a very good question to ask. Actually, it is the color is generated by the plasma, that's by the emission from the energetically excited atoms. So each gases has its own colors. You can see here the CF4 having the blue color, but the F6 having a pale blue. But if you change other gases to the nitrogen, it becomes like red or yellow. That depends on the pressure or maybe the power that you are giving to those gases. And argon is a dark red, but sometimes you can get the argon plasma even in a pink color also. That depends on the supply of the energies. So the gases gets the particular energy, so that it can transport, it can ionize at that particular energy, so that there it gets its individual colors. So since the energy levels in the gases have different energy transitions, every process gas exhibits different characteristic emission that gives the emission of this color. So according to that, the plasma color has been achieved. So you can see here the various colors of the plasma. So the argon plasma, it mentioned there as a red color, but you can see here as a pink color. That depends on the source that we are using. And if you are using the RF source, it may be like this color. But if you are increasing with the frequency of the gases, suppose it's a microwave, it may changes its color. And you can see with the oxygen plasma, it's like the whitish bluish color. The hydrogen also looks similar to that. But when you here see the methane, hydrogen, argon with varying in the pressure. So this will be with the low pressure, You can see this may be a violet color, but the top of the plasma looks like green. But when you increases the plasma ball size also increases, and also the color is changing from the dark green to another fluorescent green. So you also see with the addition of two gases also changes the color, like xenon having a light green, but if you go to the xenon plus nitrogen showing here that fluorescent color of like that green color. So depends on the gases, will get different colors of the plasma, and variation in the parameters like pressure, energy, as well as the temperature, we will get various colors in the plasma. So these are the basics of the plasma, and where we can apply this plasma technology. There are various applications in the plasma technology. The one is the plasma etching. Suppose you like to fabricate a nanostructures, we can follow this plasma technology, which is a dry etching plasma etching technique without any chemicals. We can etch out and make some nanostructures, and we can control the plasma conditions to get a very uniform or various nanostructures also. Also, plasma can be applied for the implantation purposes. For some particular ions can be implanted inside your material, or you can do a surface treatment by your material, or some in a surface level, maybe like 3 to 5 nanometer, you can implant this material. Usually in kind of plasma cleaning can be done, in which you want to change the plasma in the surface of your material by hydrophobic to hydrophilic, can be done by this, or removing some unwanted material on from your surfaces. We can do this plasma technology, so that you don't need to follow any kind of chemicals here. This is very, very safe, and even with the low thermal plasmas we can use it. No need to go for the thermal plasmas. And also we can use these plasmas for the polymer deposition also like the other kind of metal or metal oxide depositions, plasma can be applied. So these are the various plasma technologies even we may know here, but I'm going to talk about the microplasma in this work. But before that, I would like to show the applications of the plasma. Even in your kitchen, you can see the plasmas based components that we are using. Suppose you have a plasma TV there, and you have a coating here with the plasma, and we are having some shirts that we are also, you can see the 6th one with the plasma laser cut cloth. There's also there is a plasma. So each and every component in the kitchen can be fabricated or maybe coated or developed, or maybe plasma is still there in that one. Even in microwave oven, we are using the plasma with some particular frequency. So we are living with the plasmas every day. So now I'm coming to the main topic, that is microplasma. Why we are calling this microplasma? Because the dimension of this plasma is very small, with ranging from tens to thousands of micrometers. And this microplasma can be generated at elevated pressure to atmospheric pressure or higher also. And you can see some different spots of this. You can see each one is a cavity that can generate the plasma, and the colors of the plasma can be varied by different gases. So this is a microcavity arrays in which we can generate the microplasmas here. So this is a very interesting technique we can develop in your lab also by atmospheric pressure or maybe some particular vacuum. So before going to that generation of the plasma, some basics should be known. The important term is the breakdown voltage that is obtained by this passion cow. You can see that we have some 2 electrodes separated by a particular distance and supply a voltage to the cathode. The emission of electrons from the cathode will react with the gases in that chamber that creates the plasma. So there is a breakdown in the voltage. That is called, what is the breakdown? It means the generation of the plasma at a particular voltage. The moment that the discharge happens, that means the plasma generates or the ignition of the plasma happens, that is called as the discharge. So you can see from this passion cow, you can see this is the breakdown voltage and this is the pressure and the distance between the electrodes. So once the plasma starts from here, this is the discharge of the plasma. Then it continuous increase in the pressure and the distance. We can see the breakdown voltage also increases. So this point we call it as the breakdown voltage. So the breakdown voltage is a function of the pressure and the distance. The distance is the distance between the 2 electrodes in a millimeter scale. So the breakdown voltage increases as the distance between the anode and the cathode also increases. So this is the breakdown voltage is a very key parameter to be analyzed when we are talking about the microplasma. So this is the microplasma device. You can see the cathode is separated by a distance. This is a capital D that we call it as the product of PD, P and small, the capital D and the small d. So that determines the discharge properties, and the D is the spacer distance, and the cathode is the anode, and the small d is the anode and the cathode distance. So this is the cavity that forms here, and the particular pressure we can calculate the pressure and the distance that will generate the plasma here at a particular voltage. So the hollow cathode design makes them very stable and efficient here, as the capital D values between the two cathode distance increases, the operating pressure will be also increases, and lower that one it is possible to sustain the plasmas at pressure equal to about 1 atmosphere. And you can see these are that kind of cavities. So this is the capital D and the anode and the cathode. So people have made some cathodes, micro cavity cathodes. So the generates of the plasma at these micro cavities. You can see there are many arrays of micro cavities here, and this is the flexible device. This is the device fabricated in a flexible way, and this is the cavities that prepare the formation of the plasmas. So this kind of array will be helpful for the many applications in which if you want to make some plasma treatments for various in the various fields, actually basically on the plasma medicines people are using. I will touch up with these advantages of the microplasma in the later slides. Now, how we can generate the microplasmas? There are various methods. You can follow various fabrication of the cathodes, or various like what you can say with the sandwich technique. Also, we can vary the structure of the cathodes or modifications in the anodes. We can generate the plasma. So you can see here as a cathode boundary layer in which this is the anode and the cathode, so which is separated by a dielectric material. So there is a cavity here. So this cavity will have 0.1 to 10 millimeter in which we can generate the plasma in this area. Also, we can make as a inverted square pyramidal structure in that cavity. Also, we can prepare the we can make the microplasma in this cavity. And even anode can be make it as a cavity sphere with the separation of a dielectric between the anode and the cathode, that is called as a capillary plasma electric discharge, and a micro hollow between the anode and the cathode that can also generate the plasma. So these are the various microplasma generation method, and this is a very interesting one, that's a square, that's a microstrip microplasma with a microstrip parameters in which you can see, which is like here, even you can see such kind of microstrips even in our some kids can play around with these microstrip cavities. That's a plasma will be generated by a spark or give some actions to that one, the gases will get ionized easily. In that case, in that thing, they have used such kind of coils in what they separated the anode and the cathode by a dielectric material in which the discharge can be happen, so that the supply of energy, it can create a plasma in a ring. There are some plasma generated such kind of things you can see in lights also, like neon based plasma based microplasma lamps can be developed by these microstrip microplasmas. So another thing is the dielectric barrier discharge schemes. This kind of plasmas can be generated by the variation in the anode to the cathode fabrication methods, in which we can also generate this DBD based microplasma even in atmospheric pressure to a particular pressure or in a particular confined environment also. So these are the various dielectric barrier discharge schemes. So this is coplanar type, this is the counter type. I'm going to talk about this counter type in the future slides, and this is like a coaxial type in which the plasma can be generated here, apply some more pressure or some gases, we can take out the plasma outside, so it can come as a like a plasma jet or something like that, we can get it from here. So these are the DBD based schemes to generation of the microplasma, and this is the microplasma jet, and this is the gas flowing inside the anode and the cathode the sandwich structures in which the gas can get ionized with the power source. Then the jet is coming out. So the plasma jet is coming out here. The plasma will be generated here by applying some more gas pressure. The plasma will be coming out. So this is a very good technique in which people are using this plasma jet these days to clean the surfaces. And we have recently got a project in which we are using this plasma jet to the architectural things can be cleaned in one. So people use some chemicals in cleaning of these architecturals, but we are using this plasma jet now to clean more finer without any damages in those archaeological or maybe the architectures. So these are the most advanced technique that we are doing now. That project we have recently got with this microplasma jet based techniques. So this is the another series of microplasmas can be generated, and even with this series of jet, we can change the gases in each of the jets, so that is a combination of the plasmas there will result in a different kind of plasma cleaning or plasma treatments. So these are the jet that plasma is generated here, and you can see for cleaning of any kind of materials that can be done here. So this is the microplasma device that we have fabricated at IMMT, and this is a very basic schematic diagram. This is the main chamber here, and you can see this is the device that we have fabricated kept inside the chamber. And you can see here the ITO coated glass is a anode material in which ITO is a conducting layer which will be the below. This is facing the cathode, and this is the cathode material which is coated on some silicon substrate, and there is a spacer. So this is the cavity here. That's the cavity is made on the spacer. So the complete device is kept inside a chamber, and we have created vacuum, and then we pass some argon gas inside this chamber. Once we supply the argon gas, we also pass some DC power source in which the argon gas gets ionized. How the argon gas gets ionized? We are supplying some voltage to the substrate material, so the substrate will get ionized. Substrate will get ionized. The substrate will emit the primary electrons to the anode material. So the primary electrons have some energy, so it can react with the argon gas. Then that particular electrons will ionize the argon gas and produces the secondary electrons. So argon gas, that ionized one, that became the plasma, and we are collecting the secondary electrons also. So this kind of microplasmas with the ITO coated glass will be helpful for the microplasma displays. There are some plasma display units. So those kind of applications can be developed using these microplasmas. So now I'll show you the video how we are fabricating the microplasma device in a atmospheric plasma. So this is the video developed by my student, and this is the schematic diagram that I have shown earlier to contain anode and a cathode. And this is the cathode, this is a copper plate and a spacer with a micro cavity here, and this is the anode, ITO coated glass. So now we are fabricating the devices. So the cathode is the copper, and we are keeping the anode, which is a dielectric material with a micro cavity, and we are keeping the anode there. This is the spacer here, and this is the device that he fabricated, connected with the supply to the power supply. So this is the fabricated device, and this is the tube that we can supply the argon gas to the cathode material. Even without this argon gas also we can generate the plasma, but we need some high voltage, so we are giving some argon gas. And so this the argon gas is being supplied to the that device. So this is the DC power supply. There we are turning on the DC power supply. So once we supply the voltage to the device, so the primary electrons will be emitted. So one will be for the voltage, another will be for the current measurement. So you can see the device here, the gas is supplied, so the plasma is generated here. It's a very easy setup we can develop, and the application increase in the applied voltage will increases the current here. So voltage increases, the current value also increases. So the intensity of the plasma also increases with the increase in the voltage. So we can here the parameters that to be developed is the what is the breakdown voltage of the cathode material, and how the plasma intensity increases with the increase in the voltage and what is the current that we are getting. So these are the main parameters to be developed, as well as the lifetime of that cathode material. This is the study that we are doing now at IMMT to develop a robust and also a high lifetime stability cathode material to be applied for the microplasma devices. So with these parameters, we are going to characterize this material, and this is the another device we have fabricated inside a small chamber. This is a desiccator we have fabricated, and we have also created the vacuum in this chamber, and we pass only the argon gas so we can generate the plasma here. So this USB microscope will help you to collect the magnified image of this microplasma in your system. Then with that image, the plasma image, you can calculate what are the RGB colors emissions from that. And also we have a key trace setup that we can calculate the current density versus the applied voltage. So I will show you in coming slides how we can characterize or how we can get the microplasma characteristics of a cathode material. So the first important also the first one we should know about the when you're talking about the microplasma cathode material, we should know about the secondary electron emission coefficient of a cathode material. In a micro discharge, the ratio of the surface to the volume becomes larger. So the role of the plasma surface interaction is also very important when you are talking about the surface to the volume when it's getting bigger. So that parameter is the secondary electron emission coefficient, in which this secondary electron emission coefficient depends on the pressure as well as the distance between the anode and the cathode and the supplied voltage. What is secondary electron emission coefficient? Suppose you are supplying the voltage to a cathode material, the primary electrons will emit. That will react with the argon gas and that produces the argon plus another electron. That electron is the secondary electron emission. So the material should have a particular capability that can make it more primary electrons, so that you can achieve a more secondary electron emission coefficient in which the plasma intensity will be more. Otherwise, the supply of the secondary electrons is very less. So then the plasma intensity will not be glow more. Then the device cannot withstand for a longer time. So we need a very good secondary electron emission coefficient material for getting a continuous plasma emission. So that we are working on it. So the gamma, that is the secondary electron emission coefficient, is a very important parameter when you are working with the microplasma. So this is the patient curve I have explained before, and this is the breakdown voltage we are calculating, and the increase in the applied voltage, there will be increase in the distance between the anode and the cathode, and change in the pressure that will changes the breakdown voltage. From that, we can calculate secondary electron emission value. So when you are changing this pressure and the distance value, we will change in the breakdown voltage as well as the change in the voltage of what we are supplying. According with those values, you will get the secondary electron emission, the emission coefficient values. So these are the values we have received first, like increase in the applied voltage, that shows the breakdown voltage as 220 volt. You can see the voltage is the ignition of the plasma starts at 220 volt. So that we call as a breakdown voltage. With the current density and the applied field, we can call it as a 0.22 as the breakdown voltage. Then increase in the voltage increases the plasma intensity, and we have did up to 350 volt. Even we can go higher, according, it depends on your cathode material, but lower the voltage will be good. For lower the voltage in which we get some better plasma emission will be much better. So we have see here the breakdown voltage of our material, it's around 0.22 volt. This is a particular diamond material I'm talking now, but we'll discuss about more different materials and how we are going with the diamond thin film. So we are calculating the breakdown voltage here where the plasma emits, that's the breakdown voltage. And then we calculating also the breakdown voltage from the current density versus the electric field curve, and we are also calculating the current density at a particular applied field. Like if you calculate a 0.32 volt per micrometer, the current density we have observed is nearly 5.8 milliampere per centimeter square. And another parameter is the RGB values, the intensity of the RGB values. We are collecting the plasma images through a USB microscope to our system, and using some software, we are calculating the intensities of the red, green, and blue. So from that, we can also find what intensity is really higher. So you can see that RGB values can be calculated with different diamond thin films here, and the molybdenum bulk, that is also cathode material, we have compared with the diamond, and the cathode, that molybdenum cathode shows here very poor breakdown voltage, yet a higher breakdown voltage, but others shows a very good plasma emission. And the third thing, from the plasma, we are calculating the emission intensities. Suppose we are using some argon gas, so we can get the argon lines from the optical emission spectroscopic techniques. So this is a very small micro cavity. So we have fabricated a probe in which that optical probe, that is made by a fiber, that optical probe can take the intensity of those argon plasma that can be calculated, shown here. So these are the argon lines obtained from the optical emission spectroscopy. Also, we can see intensity of the plasma increases. The spectrum that we obtain from the argon lines also increases. So intensity values also increases. So these are the next study that we can characterize the microplasma. And the third one from the OES, this is the optical emission spectroscopy of the argon lines. From here, using these equations, we can calculate the electron temperature. So the electron temperature is very important in a plasma. This temperature, what we are measuring here, that will be nearly around, it's a room temperature plasma only. So we are not getting it's like not like a thermal plasma, but the electron temperature is much higher actually. So what we are getting the electron temperature of 0.6 eV, and then they have also calculated the density versus the energy. We can calculate the electron temperature from here using this equation. So the electron temperature what we have calculated for the argon lines is 0.6 eV. So this is it much compared with the argon electron temperature from the other plasma generation systems. So the third is the electron density that we are calculating from this current density values of the plasma. So the density of the plasma is really important, in which how the density depends. According to that, the intensity also increases. So you can see here increase in the voltage, the density also increases, which is parallel to that of the current density values. Next is the lifetime stability. When you are taking a cathode material, people are working on, still we are working on this to get a high lifetime cathodic material. When you are talking about the electron emission, even when the field electron emission occurs for the FESEM or maybe for the transmission electron microscopy, the lifetime of those cathode like a LAB6 or from the carbon nanotubes is degraded in few years or maybe in few months. So we need a very stable cathode material for the electron emission when you're talking about the primary electrons. So, but when you're talking about the microplasma, the plasma can etch out the cathode material very easily. So the lifetime of that material is degraded very quickly. So that material should withstand that electron emission, and even in that plasma environment is very, very difficult. When you are supplying some other gases like hydrogen or maybe some oxygen, those are all the etching gases. So it's very difficult to withstand the plasma for a longer time because the material will etch out completely. In that case, we need a highly robust cathode material. So we are when you are fabricating a microplasma device, the lifetime stability is an important parameter to be discussed. So far I have shown about the how to characterize a microplasma device when you're talking about a cathode material. So what are the materials people have used so far? People have used the copper, molybdenum, and then zinc oxide and other oxide based materials. But those materials cannot withstand for a longer time, and it needs a high breakdown voltage. Those is very much needs a high applied voltage more than 600 or 700 volts. Then we need to consume more energy. So then people start to work on the carbon based materials, because carbon nanotubes, graphene, those are all having a turn on field in the field electron emission is less than 1 volt per micrometer. So you can see carbon nanotubes is a very good field electron emission based material. So we have also tried to use this microplasma based carbon nanotubes as a cathode device. But major problem we observed with this microplasma based carbon nanotubes devices, in which that the carbon nanotubes is a good primary electron material, but it cannot withstand in the plasma for a longer time. So the uniformity of the plasma emission is very less. It can emit with low applied voltage, but the plasma is not very uniform. And you can see the bare carbon nanotubes, even at 400 volt, it shows only very less lifetime, and the plasma intensity is getting less as compared to the 0 second. So the carbon nanotubes having the poor stability. And we also tried with the carbon nanowalls. We tried with the graphene film with a thickness of like less than like 10 and 20 nanometer, but within a second it was etched out. Once the plasma emits, the graphene was completely etched out by the plasma. So what we have did with the graphene nanowalls with thickness of 1 micron thick, and even though it has a very poor stability, you can see it has here breakdown voltage of 400 volt. Plasma emission is okay up to 540 volt, but the graphene nanoflakes are completely etched out by the plasma within like a 30 minutes of electron emission. So we need a high electron emission material in which it can withstand in the plasma for a longer time. So people have suggested to go for the diamond thin film because it's a robust material, harder stone material, and it has a very good breakdown. It has a very good threshold voltage also, and also diamond is a very good electron emission based material. People are working for the field electron emission based devices. So we started working on the diamond thin films using a microwave plasma chemical vapor deposition system. We have developed the diamond thin films. So by variation in the gases, input gases in the generation of the diamond thin films, we have developed various morphologies. The like ultra nano piston diamond films, it's called as UNCD. The grains are nearly 5 nanometer size. And next is the nitrogen doped UNCD, which having a wire-like granular structures, which is electrically conducting in nature. And this is called as a hybrid diamond combination of UNCD and NUNCD. So variation of these morphologies of diamond thin films as well as the microstructure also varied a lot in these diamond thin films. We developed the microplasma devices, and these are the intensities of the organ lines that we have developed. And you can see here with the hybrid diamond showing a lifetime stability of more than 4 days, it is uniformly emitted. So you can see here with the applied voltage of 1 volt on 0.5 volt, the plasma is stable even up to 4 days. So it is a very good electron emission material compared to the other carbon based material, and this current is still stable. It keep on in a stable way. So the current is also very constant emission. So the plasma intensity is also stable. So diamond thin films is a very good cathodic material to be utilized for these microplasma devices. Also, we have carried out with different nanostructures in these diamond. One-dimensional nanostructures were fabricated using a plasma reactive ion etching method. And these are the nanostructures obtained from different morphologies diamond. And we also got a very good plasma results in which the UNCD nano pillars or some nano cones showing some very good lifetime stability of more than 6 days. So depends on the microstructure as well as the nanos as well as the morphologies of these diamond thin films that determine the microplasma illumination of this diamond based material. So far this is the best report, like 6 hours of continuous electron emission without any degradation of the current, which is very much helpful in microplasma based illumination or microplasma based display devices. And we have made some fancy carbon hybrids in which graphene, carbon nanoglass and diamond as a hybrid material. And you can see this is the diamond and this is the carbon nanoglass. Basically this is like a carbon nanotube, but we made some coloring in the FESCM images. We make it as a carbon nanoglass and some diamond soils. We observed that these hybrid materials having a very good electron emission with a very good microplasma based uniform lifetime stability of 545 minutes. So where we can apply these microplasmas? Basically, the cathode material is a very good, very important one compared to the anode based material. if you are looking for some microplasma illumination display devices, but there are other applications can also be focused. So you can see here with these microplasmas, we can make some microplasma devices, what I have shown here as a microplasma displays, but we can also use these microplasmas for the device fabrications as well as for the exploration of your new materials. So this kind of very advanced techniques are going on with this microplasma, because these microplasmas are not a thermal plasma, they are non-thermal plasmas, easy for fabrication. We don't need high power for that. If you see like RF sputtering, RF power source, or maybe with the microwave plasma based techniques, this microplasma just need a DC power supply with a minimum voltage. We get the microplasma, and but we can utilize this microplasma for the generation of for the production of various novel materials, as well as to develop a novel technology in the fabrication of the devices. So you can see the various applications of these microplasmas, especially people are working on this plasma medicine these days for the wound healing technologies, or we can also make these microplasmas for cleaning of your like various chemicals are involved in your like if you go for some surgery or something, but with these plasma techniques we can heal that wounds, or maybe we can clean those kind of unwanted things in your body using this plasma medicine. And people are using some gases, as we mentioned, they use some lasers from these microplasmas, and you can see a plasma for surface treatment in NAL, National Aeronautical Laboratory in Bangalore. They have this plasma surface treatment using these microplasma techniques, and this is the very good plasma displays from Panasonic, and this is the fluorescence lamp, and they have a spark gap between this plasma. So various technologies are developing here, and I will touch up with some of the applications today, in which this is the human skin which is touched with these microplasmas that good for the wound healing. And here you can see we can develop the nanoparticles using this microplasmas with some combination of the this is the microplasma, the generated the bimetallic nanoparticles. Then it can be flowed to a furnace. Those nanoparticles will help to the development of the single wall carbon nanotubes, which acts as a catalyst. And recently, people in US, they have developed the ultraviolet UV spectrometer generation of this, because developing of this plasma will be in the range of UV. If you supply the gases according to the range, then we can detect use as a spectrometer also. And we can also make some devices in which some displays can be developed, in which you can see the front view with a dielectric barrier supply of the gases. We can get the anode and the cathode there, and the plasma can be emitted from that one. So this kind of display devices can be fabricated using this microplasma. And this is the flexible microcavity. Currently in IMMT, we are working with the graphene flexibles, in which we can develop this kind of flexible displays with variation in this ITO coated glass or some phosphor coated glass. So we are working on some of these flexible microcavities using this microplasma devices. Now we are currently working on some graphene as well as some diamond coated graphene flexibles for these microplasmas applications. So this is the developed one in micro electromechanical devices, in which we can utilize this arrays of microplasmas can be generated here in some glass tubes. This is a flexible device. You can bend it on a glass tube, so that we can easily achieve a flexible microplasma device. And people in University of Illinois, they have developed the microplasmas plasma lamp. This is the heated part illumination. These are all microplasma lamps. So the intensity is very high. It requires less voltage, and it can glow for a longer time. So this is the very real applications made by the Professor Redel group in University of Illinois. And also we can develop various noble nanoparticles using these microplasmas. We don't need more chemicals, and also we don't need to supply more energy. Even with the plasma environment, we can develop the various nanoparticles as well as carbon nanotubes. So as we all know that carbon nanotubes or development of a nanoparticles need some very sophisticated instruments, as well as we need to pass some high temperature or some high power to the material. to develop this carbon nanotubes or some other nanoparticles. But with these plasmas, we can develop in that particular solution itself. Then the nanocrystals will be developed, and this development of these nanoparticles will help for various applications we can utilize for these nanoparticles. And the nanoparticle size you can see here, we can optimize the nanoparticles also depends on the solution what we are using, as well as with the plasma source. And people are developing the multi-layer coatings also with these plasma arrays with the different plasma gases. And recently the diamond nanoparticles can also be developed by the microplasma jet. So usually diamond can be grown with a microwave plasma of around 2.45 gigahertz, but this frequency of this microplasma is very less. And even with this atmospheric plasma jet, we can develop the diamond crystals. So there are more applications coming out from these microplasmas. So some other some graphene quantum dots and metal nanoparticles, and also they have fabricated some microplasma fabrication of this copper oxide electrodes. So more applications are developing these days with this microplasma. So this is a hot topic in the development of the nanoparticles as well as the fabrication of the microplasma devices. And now some of the applications you can see here. This is in Nigeria, people are using this and they are using these microplasmas for the taking improving the lifetime of the what I would say that the fruits. Actually, we are working on one project recently that we are working on the dielectric barrier discharge plasma to improving the lifetime of some seeds. We are collaborating with Odisha University of Agriculture and Technology. They are giving some of their seeds that will in doing with the plasma treatment, we are improving the lifetime. So during the packaging, when you are operated with the plasma, the lifetime of those packaged food materials withstand for a longer time without any chemicals. So this is the plasma treatment carried out in Nigeria. This is a real one. With the plasma environment, you can see the fruits having a more lifetime, but without plasma treatment, the fruits cannot withstand for a longer time. And another very important one is the electromagnetic devices can also be fabricated with this microplasma. So another applications from this microplasma based devices. And there is another application in the bio. There are these microplasma pattern surfaces can be developed in which we can locally make the cell attachment, and also we can make it proliferate. So many applications can be done with the bio. So we can selectively use those cells at a particular stage, and the microplasma will be emitted in that one. So the proliferation can be happen for those cell attachments. And then now I'm talking about the research that is going on in some institutes in the all over the world. There's a group in University of Illinois I have mentioned earlier. They are working on this nanosensor group. So this is a spiral based microplasma channel, and this microplasma device, the flexible one they have developed, and this is the microplasma based lamps. They can make it in the glowing lamp, they can make it. And another group in Tufts Plasma Engineering Laboratory, they have made some 3 MSS microplasma sources in which it's a spiral one, in which we can generate the microplasmas here. So even we can make a macro scale microplasma device or some miniature one of this microplasma with various applications. So variation in the pressure, you can see the intensity of the plasma increases, in which the strip can has a very good glowing discharge in that microplasma. And there is a CVD diamond film group, University of Bristol, with Professor Paul May is working on using this diamond thin films for this microplasma device. This is the diamond cavity they have created. From that, they have got the very uniform microplasma here. And laser writing can be done using this. People use the laser writing to get some patterning, but plasma can be also used for the direct lighting to make some nano patterns. This is done by the Case Western Reserve University. So this is a very interesting one that we can selectively make some patterns on your material with the plasma, which is more advantageous because it will be in a lower dimension, as well as the surface of your material will not be damaged a lot. Otherwise, if you go for some patterning with the drying method like reactive ion etching or maybe the chemical wet method, or you are going for some nano pattern methods, will requires more energy, like more etching process. But this is no etching, only surface can be treated, we can make the patterns. And there is University of Notre Dame, they are also going on this Go research group. They are working on these microplasma based devices for fabrication of the micro electromechanical systems. You can see they have made a nanostructured device in which microplasma can be generated between the two cathodes. So now I'll talk about the microplasmas fabrications as well as the materials involved and the various research activities all over the world, and where microplasma has been applied and what are the applications. So the microplasma is a new field in India, but it has more good future in the near future. So we can develop. It's a very upcoming field in India with a miniature. Apart from this microplasma, here I would like to show some of the facilities in my group. And this is a most advanced technique that we have is a laser-induced graphene, in which we can grow the graphene instantly on a polymer substrate. So we can get the flexible graphene instantly within a second. And this flexible graphene we are using for the microplasma cathodic devices. And this flexible graphene has more various advantages in terms of energy, environment, and also for the sensing-based applications. And these are the other facilities in my group. I am an electronics guy, electronics material engineer. So we are working on Hall effect measurements, core probe measurement, and we have a gas sensing system. And we have also having a photocatalytic studies apart from the other central characterization department. So from here, I would like to conclude my talk. And so looking forward for a very good collaboration with SRM. Actually, we have initiated a MOU between SRM and the IMMT. Is the MOU is under process, and so we are looking forward for a fruitful collaboration with SRM in the near future. So you may contact me for a future collaboration. This is my email ID and my phone number. So finally, I would like to thank again the organizers of this faculty development program for inviting me, and it's a good opportunity for me to show some of the applications of microplasmas and the development of the cathode materials for the microplasmas and some of the upcoming activities and in my group. So thank you all for your kind attention.
Sir, thank you so much, sir. Thank you so much for your nice presentation. And you have explained about plasma, microplasma, how it is, what are the generation methods you have explained, and you have explained our device fabrication you have explained us, and also the characteristic applications. I'm really astonished to see the applications of microplasma. Thank you so much, sir, for your presentation.
Thank you, Dr. Sankaran, sir. It's a very useful and wonderful talk about microplasma research, sir.
Thank you, sir. Thank you, sir.
Yes, sir. Yes, sir. Yes, sir.
Thank you, sir. Really, it is a wonderful talk, sir. Thank you so much, sir.
Yes, sir. Yes. So, any questions? I am happy to answer.
Sir, am I audible?
Yes, yes, you are audible, madam.
Sir, can you please do me one favor, sir? Can you please share your email ID in the chat box, sir?
Yes, madam. I will share it immediately.
Dear participants, if you want to have any collaboration or if you want to have any doubt, if you want to clarify any doubt with the professor, sir, you can contact through this mail ID. So any doubts, any questions from the participants, you can please raise your hands and you can ask your doubts. Shar has shared his email ID. You can contact him through mail regarding your doubt clarification, or if you want to have collaboration research work, you can contact him through his mail ID. Any questions? Dear participants, do you have any questions? You can raise your hands and you can ask your doubt to the resource person.
Saravanan sir?
Yes, sir.
3:30, the another program.
Yes. Thank you, Sankaran sir. Thank you so much for being with us.
Yes, sir. Yes, sir.
We have already initiated that MO process under Maitri.
Yes, sir. Please.
Okay, it is under progress. Hopefully, okay, we will be succeeded for that one.
Yes, sir.
Thank you
Sure,
so
sir.
much for your cooperation regarding this, sir.
Yes, sir. Yes, sir. Thank you so much, sir. Yes, sir.
Thank you,
Thank
sir.
you. Thank you.
so much, sir.
Thank you so much.